Hey Phys 1 kids, Campbell here. In our third video in one-dimensional kinematics, we're going to talk about graphing motions more. Now, we've already talked about position versus time and velocity versus time graphs. We haven't spent any time on acceleration. Now, in this class, we're always going to deal with constant acceleration. And there are three types of constant acceleration. Either we have constant zero acceleration. So if we graphed an acceleration versus time graph, it would just be a graph of zero, a flat line on zero. Constant positive acceleration, again, if it's constant, it means the value isn't changing. So once again, it's a flat line, but this time it's positive, so it's above the 0 point, above the x-axis. And of course, constant negative acceleration, again, constant means constant value, but negative, so below the x-axis. But what does this mean for velocity? Well, if we have zero acceleration, right, that means we have constant velocity. The velocity of the object is not changing, which means we have that constant horizontal line on our velocity versus time graph, and that slanted but straight line on our position versus time graph. But if we have acceleration, well, then things get crazy, right? Because whether I have positive or negative acceleration doesn't tell me anything about speeding up or slowing down, right? It depends upon what direction I'm going. Remember that from our first video, we said that positive acceleration could be speeding up in the positive direction or slowing down in the negative direction. And that negative acceleration could be slowing down in the positive direction or speeding up in the negative direction. Oh my gosh, speeding up, slowing down, positives, negatives, craziness. Well, let's talk specifically about speeding up versus slowing down. If an object is speeding up, right, that means its velocity is increasing as it travels. And one way, if we're looking at vector diagrams, the velocity and acceleration vectors, when they point in the same direction, it means that an object is speeding up. So if I have a positive velocity and a positive acceleration, then I am speeding up. How do I know I have a positive acceleration on a velocity time graph? Well, if the slope of a velocity time graph is acceleration, then a positive slope would mean positive acceleration. Now, a position graph is a lot trickier. One of the things that we'll see, right, we know that it's speeding up because its slope is getting steeper with time here. And if it's getting steeper with time, I must be increasing the slope, increasing the rate of change, so increasing my velocity. Interestingly enough, we'll see that we get this positive concavity here when I have positive acceleration. Have a negative velocity and a negative acceleration, so they both point in the same direction. Negative times a negative is a positive. Then I am speeding up. And if I look at my graphs of position versus time, you can see in the positions, again, notice how the slope gets steeper as I move, which means if the slope is getting steeper, then my velocity is increasing in magnitude from some number, 0, say, to some higher number. Again, negative slope on a velocity versus time graph means negative acceleration. But I can have negative acceleration and speed up. Oh my goodness. Well, for objects that slow down, the velocity and acceleration vectors must point in the opposite direction. So, for example, if I have positive velocity but negative acceleration, then I'm slowing down. And if I look at a position versus time graph, notice how the slope is decreasing. It's getting flatter as I move, which means that if the slope is getting less, that my velocity is getting less. So I'm decreasing the magnitude of my velocity, which you can see by looking on this graph. If I have a negative velocity and a positive acceleration, then again, my slope, I'm slowing down, right? Because my slope is getting less. But this time it's negative velocity. Remember, negative velocity doesn't mean anything about speeding up or slowing down. It's about the direction I'm moving. So if my slope is getting less on my position versus time graph, I must be slowing down. The change in velocity must be getting less. And in this case, I have velocity going towards 0, right? Even though I had negative velocity, I'm going towards 0, which means I'm slowing down. Now, there are times when you're going to have to look at these graphs, a position versus time graph, for example, and say positive or negative acceleration. And so you could be like, oh, okay, speeding up in the positive direction, slowing down in the negative. Wait, what way am I going? Well, I have a trick for you. On a position versus time graph, if you have positive concavity, so like happy face, that means happy face, that is positive acceleration. If we have negative concavity, which is like a sad face means negative acceleration. So positive concavity, smiley face, positive acceleration. Negative concavity, sad face, negative acceleration. And of course, if there's no concavity, if it's a flat line, then the acceleration is 0. So that's a good trick. Happy face, sad face, just straight line. Which is it? All right, so let's see if you can figure out about speeding up, slowing down, positive, negative velocity, and acceleration from these graphs. So what I want you to do is you can see this in your packet, I want you to pause the video and look at the graphs and figure out if you can get these answers right. There may be more than one correct answer for each of the numbered questions. So let's check your answers. In order for an object to have positive velocity, that means on a position versus time graph, I have to have positive slope. Now, I know these slopes are changing, but if you look at A and B, you'll notice that they're slanted up. Even if you took a tangent line, the line would still have a positive slant to it. So that would be a positive velocity. For number 2, it asks which have a negative velocity. Hopefully you said C and D, because if you look at the slope, even though it's changing for C and D, those have negative slopes. For ones that are speeding up, it's A and C. How do you know? Well, what you're looking for is an increase in the slope. So here the slope is getting steeper and steeper and steeper. If we drew like a bunch of different lines, tangent lines, you'd see that those lines get steeper and steeper as we go. Same thing here with C. If we draw some tangent lines, you can see that it gets steeper as we go. So steeper means we're speeding up for a slope. If slowing down and then is B and D, because you'll notice that they start to plateau. So anytime my line plateaus, that means I'm slowing down. That rate of change of position is decreasing. For 5, hopefully you got this right. Which ones have smiley face, right? Positive acceleration, smiley face. So that's A and D, right? It's like a half of a face here. And frowny face, negative acceleration is B and C. How'd you do? All right, now we got to talk about areas under graphs. Now I mentioned this in our last video, that the area under a velocity versus time graph is position, because the area under a graph shows what's being built up over time. Now, just a little review of area equations. The area of a rectangle is just base times height. The area of a triangle, right, is 1/2 base times height. And you're going to need those equations because we're going to be calculating some areas. Now, one of the cool things is any physics equation that is something times something, so x times y, we can use the area of a graph of those variables to find the desired quantity, because x, that's my base, y, that's my height. Base times height is area, so something times something, that will give me some quantity. For example, if we arrange the average velocity equation, velocity is position over time, or the change in x over change in t. If we solve for the change in position, we get velocity times time. So that means that the area under a velocity versus time graph, right, there's velocity on the y-axis, time is on the x-axis, base times height, the area is going to give me the change in position, or the displacement. So let's take a look. We've already talked about slopes. Let's talk about areas. Area, base times height. So if we look at this acceleration graph here, and I rearrange the velocity acceleration equation, right? Acceleration is velocity over time. So if I rearrange that for velocity, acceleration times time is equal to velocity. So that means that the area under the acceleration times time graph will give me the change in velocity. So in this case, I have, if I just shade in that rectangle, the area under the curve is the area between the line, the data line, and the origin. So if I shade in this, say I want to know what was the change in velocity from 0 to 2 seconds. Well, base times height, this is a rectangle, 4 times 2 is 8. So the change in velocity was 8 meters per second. Or if I want to do the whole time, right, then my base is 5, my height is 4. 5 times 4, 20. So in 5 seconds, the velocity change is 20 meters per second. Same thing if we go back and graph to the velocity graph, right? If velocity is position over time and I rearrange that equation to get position is equal velocity times time, that means that if I have a velocity graph and I take the area, that data, whatever that comes out to be, is going to give me the change in position. So areas are very handy tools. So the area under an acceleration graph gives you velocity, the change in velocity. The area under a velocity time graph gives you the change in position or displacement. Handy, handy, handy. So let's practice that. So here is a velocity versus time graph, and I want you to calculate the area of each of those segments. So pause the video and calculate the areas. If you do that, right, here's our first area, and it's a rectangle. Now, one thing I want you to note here, any area that's above the x-axis are positive, and any area below the x-axis are negative. Remember, a negative velocity means I'm going backwards or in the negative direction. So here I have a -2 times 2, right? Well, that's a -4. So I must have traveled -4 meters during the first 2 seconds. In this time period, I have 0 displacement, right? My velocity is 0, so I'm not going anywhere. But then I have an increase in velocity here to 5, and so if I look at this area here, right, the base here is 6 minus 4, which is 2. The height here is 5, so 2 times 5 is a positive 10 because I'm positive. So if we want to know what this translates to in a position versus time graph, what I did is I took the data from this slide and I made a little table just so that it was easy for us to see. Now remember that on our velocity graph, if we go back to this velocity graph, notice those are horizontal lines. That means that's constant, which means that on a position versus time graph, I have straight slanty lines. Now, one of the problems when we go from velocity to position is I need to know where am I starting, because a velocity graph doesn't mean, just because I start at some velocity or even 0 velocity, doesn't mean I'm starting at 0 position. So here we're going to have to make an assumption because I didn't tell you. We're going to assume that we start at a position of 0. And when I get to 2 seconds, according to what I found, we are at -4 meters. So we're going to draw a nice straight line from 0 to -4, because remember, it needs to be a constant slope because I have constant velocity. Now, what does it mean to have 0 displacement? Does that mean I go back to 0? No, it means I stay at -4 for the next 2 seconds, from 2 to 4 seconds. So that should be a nice flat line. Lower flat, is it? And then from 4 to 6 seconds, I travel 10 meters. Now, this doesn't mean I'm 10 meters from 0. It means I'm 10 meters from my current position, which is -4. So if I subtract -4 from here, right, that gives me a +6. So that means at 6 seconds, I am up here at a +6. And so that means I'm going to draw a straight line. And remember, it's a straight line not because I connect dot to dot, but it's a straight line because I have positive constant velocity on my velocity graph. So we're going to draw, hopefully, a nice sort of straight line to 6 meters at 6 seconds. So there is our translated position versus time graph. All right, let's try a tricky one. If I have a velocity versus time graph that's not flat, that means that the position is changing at a different rate. So that means I have acceleration. So see if you can figure this one out. Pause the video, and then let's see if you got it right. So one approach for this one is to just take areas from 0 to each individual time point. So if I do the area of this triangle here, you can see I have the calculation here. At 1 second, I take 1/2 times the base 1 times the height 1, and I get 0.5 meters. So I'll graph 0.5 meters on my little graph. And then I extend to 2 seconds, and I take this whole area, and so up to 2 seconds, from 0 to 2 seconds, my area is 2 meters, and I'll do the same thing for 3 seconds and take that whole area. So from 0 to 3 seconds, I have traveled 4.5 meters. So when I go and I graph this, there's 2 at 2, and there's 3 at 4.5, which doesn't quite go on my graph. And you can see I'm no longer a straight line. It kind of looks like it. But you should recognize that anytime I have a velocity graph that's changing in magnitude, so slanted line, not a horizontal line, my position graph is going to have a parabolic shape to it. So it'll be a curvy graph like that. How'd you do? Well, we're going to work on this some more in class, so I'll see you in class.